In this video, we're going to start talking about these ideas of empirical and molecular formulas, and I'm going to show you how to calculate an empirical formula. So the first thing we need to do is define these words. So an empirical formula is the smallest whole number ratio of atoms in a compound. This is in contrast to the molecular formula, which gives you the actual number of elements in a compound. So it represents the total number of atoms in one whole unit of the compound. And this molecular formula is always a whole number multiple of the empirical formula. So the empirical formula tends to contain the least amount of information. It's simply the ratio of atoms in the compound, whereas this has the actual composition of the compound contained within it. So for example, let's look at acetylene and benzene, so these two different molecules that are both made out of carbon and hydrogen. So acetylene C2H2, benzene is C6H6. Both of these compounds have the same empirical formula, which is CH. Once again, this is the smallest whole number ratio of carbon to hydrogen in the compound, so it's just 1-to-1 for these two examples. Once again, this is the empirical formula. So once you have this empirical formula, you'll notice that each one of these is a whole number multiple of the empirical formula. So if you take this and multiply by 2, you get acetylene. If you multiply by 6, you get benzene. So that's what it's showing down here. So let's take a look to compare these once again. So once again, here's the empirical formula over here on the left. It's just CH. Here are the two molecular formulas that contain the actual number of elements in the compound, and also here are their structures represented beneath them. So these lines are representing the bonds. So I just want to point out the empirical formula has a lot less information contained in it, once again, and I want to point out that both of these things have no information about the connectivity of the atoms. So this is a topic that you'll learn more about if you take organic chemistry. But just know that both of these things contain different amounts of information, and the amount of information is, of course, limited. So let's do another side-by-side comparison. Each compound that has different chemical and physical properties, so if there's different numbers of carbons and hydrogens in these compounds, they're completely different compounds and they have different properties, even though they have the same empirical formula. So another thing that's interesting and worth noting is that the percent composition of all of these compounds is the same, and that's because they share an empirical formula. So we said before that percent composition is independent of mass because it's kind of a ratio, and you can see that this holds in this case. But of course, these substances all have different molar masses, so a mole of benzene doesn't weigh the same as a mole of acetylene, because they contain different number of atoms. But one thing you should know is that the molar mass of the compound is the molar mass of the empirical times whatever multiple it's multiplied by. So if you take the molar mass of the empirical formula, which is just CH, this 13.02, it's equal to 2 times, so 2 times the empirical molar mass is equal to the molar mass of this acetylene here. Once again, it's because you take this formula and multiply it by 2, you can just multiply the molar mass by 2. Similar for the benzene, so you multiply by 6 to get benzene, so the molar mass times 6 is the molar mass of the benzene. And this is going to be really important when we solve problems to determine empirical and molecular formulas. So let's talk about how to do that. So let's calculate empirical formulas. We need to know some information about the compound. So first of all, we need to know what this compound is made up of, what elements are present. So that's the first thing. If you don't know this, there's really no way for you to come up with the formula. Once you know this information, however, you can always get the atomic masses of these elements from the periodic table. So that's something you definitely need to know in order to calculate this. And then, of course, we need to know the ratio of these elements in some form, either the percent composition or some kind of mass ratio, just some information about that. So let's talk about the strategy to do this. So Usually the way people do these problems is that you start with the compound and you assume you have 100 grams of it. It's just a convenient number to work with because we're thinking about percents a lot of the time, so you just want to think about 100 grams. So you express the mass of each of these elements in grams. So if they tell you that something is 50% hydrogen and 50% oxygen, you can say, I have 50 grams of hydrogen and 50 grams of oxygen. Once again, when we're dealing with the ratios and the formulas, the masses are going to cancel out in the end anyway, so there's nothing wrong with assuming a unit here. We're going to take these grams of each element and convert them into moles using the molar mass. The reason is because, once again, we're trying to get into a unit so that we can work with these groups of quantities. So these numbers can get a little tricky. Sometimes they work out to be whole numbers and sometimes not. So once we have everything written in moles, we can divide these mole amounts by the smallest number of moles present. So once again, we're finding the kind of the mass or the mole ratios between all these different elements. So we're trying to come up with the ratios. So the new numbers are going to be the subscripts that you use in the formula. Like I said, every once in a while these don't work out to be whole numbers. If they do work out to be fractions, we can kind of just multiply them by a factor until they become whole numbers, because we always want our chemical formulas to be whole numbers. So let's look at an example here. The previous slide will make a little more sense and be a little more definite. So we want to calculate the empirical formula for a compound that has 11.19% hydrogen and 88.79% oxygen. So once again, we're going to pretend we have 100 grams of whatever this compound is. So what that ends up meaning is that there's going to be 11.19 grams of hydrogen and 88.79 grams of oxygen. So once we have these amounts in grams, we're going to convert each one of them into moles using their molar mass. So for hydrogen, we can read from the periodic table that we have 1.008 grams of hydrogen for every 1 mole. So we construct this conversion factor and we convert our grams into moles here. We do the same for oxygen. So we have 88.79 grams of oxygen, and we know that there are 16 grams of oxygen for every 1 mole. So this gives us these two numbers here. So we have about 11 moles of hydrogen and 5.5 moles of oxygen, roughly. So you can see when we take the ratio of these things, there's going to be about twice as much hydrogen. So once again, we're going to divide by the smallest number of moles, which ended up being 5.549, the oxygen. So we're going to divide each number of moles by the smallest number. So what this is showing here is that there's 2 moles of hydrogen for every 1 mole of oxygen. So our empirical formula ends up being H2O. Say what's on the next slide. So the next slide, I'll pause for a moment to let you take that in. So basically, yeah, you can see that the number of moles are canceling out in the numerator and denominator. And another thing is, if this worked out to not be a whole number, so for example, if this came out to be 2.5, you could multiply each one of these quantities by 2. So this would become 5 and this would become 2, and now you would be dealing with whole numbers. So we're probably going to see some examples of that on the next slides. So here's another example. This is asking you to calculate the empirical formula for a compound that contains 56.68% potassium, 8.68% carbon, and 34.73% oxygen. Spend a little time doing that, and I will give you the solution to that on the next video.